First of all, thank you, the full organizing committee, for giving me this opportunity to deliver on keynote speaker lecture. Actually, today I'll develop the lecture on that how to develop composites material by friction stir processing technique. Okay, because nowadays these composite materials are applied in every industry, starting from the industry as well as like aerospace, automobile. Even though it is applicable for the biomaterials also. So this actually the friction stir processing is another technique to develop this kind of composites. Coming to the next slide. Okay, first, what is composites? Means everybody know that what is composite nowadays because it's a very common materials, advanced material also. So since this is advanced material, so that is the requirement of processing of advanced technique. So that is why I have chosen the friction stir processing because it's advanced technique to process this kind of composite materials. What is composite materials? It's a combination of two materials. Means one should be the matrix, just to follow the cursor, and another is the reinforcement. When both are combined together, then this is the composite materials. And that you can see the application part, mainly that aluminum based matrix, that is highly applicable for the industry, as well as magnesium, other ceramic composite also. So it's having wide application in the several aspects. And you can see the very natural source of composite. Just here I am highlighting one example only, that is bamboo piece. These are all different composite materials because you see, if you see the under the microscope one cross section of bamboo piece, you can find a lot of reinforcement that is uniformly distributed. So what we are making here, we are making the artificial reinforcement, means artificial composite materials for our application purpose. But these are all natural. So everything is coming from the nature. Taking the view from the nature, we are implementing in our daily life. So that is our motto in case of any kind of research field. So what is basically composite materials? Means what are the composite materials like polymer matrix composite, metal matrix composite, and ceramic matrix composite. So these are all the three broad classification of the matrix. Now, if you think about the reinforcement, shape, and size, then the matrix that composite material will be among the on another four categories like particulate reinforced composite. That is very simple, that particles are distributed, and that diagram also I have not shown here because it's a common thing. And flake composite, you can see that a lot of flakes are distributed over the composite materials. And the fiber also, that is fiber reinforced composites, a lot of fibers will be distributed. And the laminated composite, that is very important, especially for the shipbuilding industry, because you see one ship total structure that is made through the laminated object manufacturing process, because where the very high strength is required, if any collision any other thing is happening, so you requirement have that the high strength. So that is why the laminated object manufacturing can give a very nice solutions for that. Okay. So the function of the reinforcement here, actually this reinforcement basically is improving the overall properties, because single metal or single alloy like aluminium, single alloy cannot give the solutions for your application purpose. But if you do some kind of composite materials, means if you add some reinforcement, so that can enhance the overall properties of the composite materials. So several methods are there to, in order to fabricate this kind of composites, several methods are there like star casting, spray deposition, liquid metallurgy, powder metallurgy, and friction stir processing, as well as laser sintering. So here, just I am going to discuss about the friction stir processing technique. By this technique, we can develop the this kind of composite materials. Friction stir welding means everybody know that, because it's a solid state welding process. Basically, this welding technique will be applied to process the composite materials in another way. So friction stir welding is a technique. Just you follow the diagram, there will be one pin. Okay, the tool will be there. Actually, tool is having that. There is pin. The base is the basic material, this workpiece material, Okay, so this, suppose this is moving from left to right direction. Okay, and it's moving in the anti-clockwise direction. So this pin will be penetrating into the workpiece material, and finally it is moving from left to right direction. And in this case, the material is flowing. Means material is actually, whenever this kind of processing is going on, friction is a very big role here. It is playing because of these frictions, the heat will be generated, but this heat means the parallel temperature will be raised, but this temperature will not be sufficient enough to this workpiece material. Okay, na? It's a solid state welding because material will reach up to the plastic point only. Okay, there will be plastic flow of the materials. So that is why. So in the left side, you see this is called retreating side. In the right side, this is called advancing side. Means material will be taken from the retreating side, and this will be moving to advancing side. And this is fully cyclic process. So, and this is, you see this nugget is formed. Actually, this is the star zone. That is called nugget. Okay, so this is solder and this is the pin. So solder is continuously touching over the workpiece. This is mainly also this creating the frictions along with the pin also. Next is the parameters. Whenever you are processing something, there is a very important parameter should be there. Okay, like a tool design is a big parameter here because the tool may have pin also. This pin also may be varieties. Okay, maybe it is conical shape, maybe it is cylindrical shape, and pin may be also threaded also. And the RPM means tool rotation also another parameter to control this processing technique. And speed also important parameter, and axial force. So mainly these four parameters are very much influensive parameters to influence this full processing technique. Just here I am trying to show some the video so that it will be more clear for you to understand this basic process of the friction stir welding. You see this pin is there, solder is there, both are touching, and this will be moving. So because of the frictions, the material is becoming heated, temperature will rise, but it is not reaching to melting point. Above the recrystallization temperature, that will be heated, and plastic flow of the material will be done because material is fully reaching to the plastic zone, and that is called, this is solid state welding. There is no fusion, there is no melting. Okay, it's a simple one. So in case of this, don't mix between friction stir welding as well as processing because both principle are same, but in the other way, in an unconventional way, we are thinking to process the material. How to do that's I'll describe later. Okay, so coming to the next slide again. Okay, so you see the application already I have said you in, this is applicable for the aerospace as well as the building industry, other industry also that can be applicable. Now I am highlighting one case study for this because just the here I have talked how to form this composite. Now I have done some composite material development with the help of some scholar. Okay, so that one case study I am described now. Okay, this the fabrication of the MOS2 as well as cerium oxide reinforced aluminum matrix hybrid composite, and investigation on the effect of the process parameters. So what the alloy material I have chosen here, aluminum based, that is 7075 alloy. Okay, and the elemental composition that is also highlighted here, and the strength, several density, strength means yield strength, ultimate tensile strength, elongation, micro hardness. This is available for this, means these are available for this material. Okay, and this is the ACM morphology of the MOS2 as well as cerium oxide particles. You see the, say, just only distributions after purchasing the particles from the market. Just we have seen the ACM morphology of this particle. This is the basic experimental setup. Here you see this. This is available in NIT Agartala also. That there is a friction stir welding machine. This is a control unit. From here you can put your program and you can control full your operation. Okay. Now, what is the fabrication process? That is very important because previously I have said you the welding technique that is established already, but parallelly we are thinking to develop the composite materials. In case of this, you already previously I have mentioned composite means alloy plus reinforcement. So you have to add the reinforcement. Reinforcement is not in your alloy material. Suppose any reinforcement material like CO2 or MOS2 I have applied. How? First, I have to create one groove. Here there is no two part. Find it. In case of welding, you are joining two pieces. Understand? But here is only one piece. But at the middle, we are making some groove. Okay, that is maybe that the semicircle or some kind of V groove also. And after making this groove, we are pouring our ceramic particle inside, and whatever ceramic particle that will be spreaded over the top surface, that has to be eliminated. Okay, after cleaning the surface, just we will place this workpiece under the tool, and initially the tool will be moving. There is no pin initially because first tool should be touched with the workpiece, and because of these frictions some skin surface of material that will be moving, and because of that these groups will be filled, means ceramic particles that should not be coming out during the main pass of the experimentation. Third step, we are following that with pin. This tool is moving with pin and with some particular speed. At that time, the whatever the ceramic particles are inside in the groove, so that will be distributed over the workpiece material. So that is the main idea. Just we are distributing the ceramic particles inside the material so that it will create some composite. Okay, at the solid state also, when the temperature is reaching to some up to certain extent, there will be lot of metallurgical bonds. So the ceramic particles will not be spread very loosely. There will be some kind of metallurgical bond also. Okay, and thermocouple you can fix in order to judge how much temperature that is rising in the workpiece material. Okay, so this is a typical shape of tool that is shown here. One my scholar did like that. He used this pin. Okay, this pin is little bit cylindrical type and threaded. Okay, so geometry also is shown here. And here I have chosen few the parameters like tool rotational speed, transverse speed, number of passes 1 and 2, and tilt angle and flange depth, means how much depth the pin is inside, and the ratio of MOS2 as well as CO2 that is varying. Initially it was like 100 0, then 80 20, 60 40, 40 60, 20 80, and 0 100 in order to check the influence of this kind of ceramic particles. Okay, and this is the technique after developing. Just we have taken this sample to create some standard specimen, like suppose if you want to test the tensile strength, so ASTM standard you have to follow E8. So from this you can create some kind of specimen, as well as for the micro harness testing you can take it out some few portions. Okay, and for microstructure also and XRD also. This is the methods of characterization. Now come to the results. So here the axial force and transverse force that we have measured, that is basically just you see in the first graph, that is A 18A, the processing length continuously that is increasing, no, but axial force gradually that is decreasing, and also it is look like a constant also. Decreasing why? Because the heat is transferred through the conduction method. So the previous means previous portion of material that is just ahead of the tool, that is little bit plasticide. That is why the axial force is going down, and transverse speed also it's look like having the same trend. Okay, and now if you look into the first pass as well as second pass, in the second graph in the figure 19 you can find that there's a comparison between the first pass as well as second pass. The second pass also necessary. Why? Because I have said you in case of natural composite, the reinforcement are uniformly distributed, but we are making the artificial composite. So there is a very challenging one to distribute the reinforcement particle uniformly. That is why we are following these several passes. Maybe one, maybe this is two, maybe this is three. but not like that it will be 10, 12, 15 like that, because that will lead the other kind of defects. So it's better to choose 1 and 2, that's to get the better information, means of the distribution side, so that you can get very nicely, because you can avoid the clustering effect also. And now here the graph you can see with respect to rotational speed as well as axial force graph. Here the four varieties of transverse speed is highlighted. You can see in case of the 600 rotational rpm, you are the at the transverse speed like 70 millimeter per minute, you are getting the maximum axial average axial force. And the second graph, this is the average transverse force. In case of 600, again it is showing the maximum axial force, because the slow speed it's not giving so much friction time kind of things, so that the plasticity that is not improved too much. So because of that, force may be high. And here you see the some optical micrographs. It is clearly seen that the clustering, this is the first figure you see in the left side. The clustering means where the some reinforcement particles that will be agglomerated at a particular point, means this is not distributed over the full zone, nugget zone. And also you can see some kind of onion ring, because there is a circular motion of the material. So obviously after completion of your the experimentation, you can find some kind of onion rings. And here in the figure number E, you can see the uniform distribution of the ceramic particles. And here also you can find in the C figure some coarser grains are available. Okay, and the finer grains also it parallelly it is available. And this is the ACM morphology of the specimen. Here you can see some particles that is distributed almost in a uniform way. So that is our intention to distribute the reinforcement particle, because what is the role of reinforcement here? Because whenever you are applying some force into composite material, basically this string means this force will be transferred to the reinforcement also. So this reinforcement will help to withstand this kind of load. So that is why the reinforcements are spreaded in the composite material. Here also you can see the distribution of the MOS2 as well as cerium oxide that is distributed in the composite materials. This is the XRD graph, already you know this. Here you can see some, this aluminum is existing, MOS2 as well as CO2, obviously it should be there, as well as some intermetallic compound also you can find. So that indicate there is a lot of metallurgical bonding is happening continuously. Okay, and this is the graph basically that average grain size with respect to rotational speed. Here one beauty thing is that at the 600 rpm you are getting very good grain size, and parallelly at the end. And because of this, basically this here the heat generation is playing very important role in case of this heat generation, because the because of the temperature, the grain orientation will be happening always. So because of that only this average grain size are varying with the respect to the rotational speed. And this is the for the first pass in the figure A, and in case of figure B, this is for second pass. Okay, because in the second pass you are finding that average grain size is less, because at that time the whatever grains in the first pass that is created, again that is reformed and trying to provide the more finer grains. So because of that this average grain size of this case in the second pass that is less. And that is the tensile behavior. Just you see, we have processed the material, it's showing fully ductile in nature. Okay, and similar to ductile, yield strength also very improved. Okay, for the first pass that is blue line, and second line for the that is the second pass. In case if you compare between first pass and second pass, you can easily it is visible that overall yield strength and other properties that is improved for the second pass, because of the overall distribution is well, that is why. And if you look the fractured surface under the ACM, so you can see a lot of dimples and fractured particles also you can see. Okay, and this is basically ductile fracture is happening in case of tensile failure. Here the typical the graph that is between the yield strength as well as rotational speed for the first pass, and this is a second pass. Here also this the typical variations with the UTS value as well as rotational speed for the first pass as well as second pass. Okay, so that here for the 1200 to 1500 rpm it's showing the better yield strength, and in case of this UTS value for the 1200 to 1500 it's showing the better UTS value, and the second pass it's showing the better results because of the overall distribution is well. And this is the elongations, obviously that there is also same trend we are following, but in case of, you see this, in case of second pass elongation is little bit less, because any material, if the, in case of first pass, that it's the material is little bit ductile. So ductility basically in the second pass that is dropping. Okay, because thing is that on the, if you think about the reinforcement materials, means these are all ceramic materials, fine. So the ceramic materials is nothing but the brittle materials. So brittle materials is having the low ductility, very few, very simple. So here in the second pass, the, because of the overall distributions of the particles, the overall ductility it is becoming less, but the, but overall other properties, like other different properties like hardness, corrosion resistance, wear resistance, these are improved. So we always, we are looking for a moderate level of different properties, because for your application purpose you are not requiring only the ductility should be very high or UTS should be very high, like that. You should requirement of the good UTS value, good yield strength, good corrosion resistance, good wear resistance. So in this way, you have to develop some kind of product which can offer you the, in all respect, that is good. Okay, and you can follow the microhardness value also. The previous case, that in the previous diagram you see the elongation that is decreasing in case of second pass, but if you think about the microhardness value, here you can see the, for the 1200 to 1500 the microhardness value that is increasing. So that is good. In the previous case that is not good in the first pass, but in the second pass it's offering good. So that is why it's, you are getting a moderate level of other properties. Now think about the wear behavior, because this is having a high application in the shipbuilding as well as aerospace industry. So wear also another factor, because the, otherwise material will be worn out very quickly. Okay, so if you compare between the friction coefficient with the rotational speed at the 600 as well as 800 is showing better results, and the second pass also the 600 and 800 is showing the better results. So in case of friction coefficient, so naturally, if the coefficient friction is high, means the, here also you can see the specific wear rate, that how it is changing, means 600 to 800, that is 1800, that is at the level of 600 the specific wear rate is very high, at the level of the 800 also the specific wear rate is very high, but the 1200 to 1500 this range can offer you the better results in case of wear resistance. This is the wear track diagram, means the SEM morphology of the wear track. Here you can see the, how this kind of sliding wear is happening, like sometime adhesion is there, sometime grooves are there, because material is flowed from the particular space. Okay, so this is this kind of it's a look like of the abrasive wear is happening, because reinforcement particles are there. So these particles will be coming out, and this will act as a abrasive. So because of that, this kind of wear is look like a abrasive wear. Okay, because the wear testing, you know, there will be some kind of pin will be there, and this will be rotating over the surface. So in between pin as well as workpiece, if the abrasive is coming, so that will create the wear. Okay, so this kind of wear is happening. Corrosion resistance is very important. Suppose you are using this in the shipbuilding industry, so it will also this ship in the water. So there may be some kind of corrosion may be started. So that is why we have tested the corrosion resistance also, corrosion potential and corrosion current density, that we have tested. This is the varying with the rotational speed because of the overall distribution of this reinforcement, because MOS2 and CO2, this is having very nice reinforcement in case of the wear resistance as well as corrosion resistance property. And here you can see the corrosion rate, how it is changing. So 600 and 1800 we are getting the better results of corrosion resistance, and in case of second pass also we can have the similar kind of trend almost. Okay, that in case of 600 and 800 we are getting the better corrosion resistance. So the inferences like the effect of the process parameter, basically the second pass is very important here. It's playing a very good role, and it's offering you a good distribution of the reinforcement particle. In order to attain your main goal, you want to get success to develop this kind of composite materials with the help of the friction stir processing technique. And the particle distributions improve with increase of tool rotational speed and reduction of the transfer speed. And highest tensile strength microharness wire resistance is obtained for the composite, that is for 1500 to 40 millimeter per minute, and for the second pass. Okay, and second pass composite show the inferior corrosion behavior due to the fine grain structure, as the grain boundaries create the micro galvanic couple. ठीक है ना? So the second pass is showing the better results in case of all respect because of the overall distributions of the reinforcement particle in the matrix. And here also that you can attain the wear and corrosion resistance of aluminum alloy is enhanced. Okay, the tensile strength, that is 92% and micro hardness 90-80% is reduced compared to the as received alloy. Okay, and the composite with best tensile strength and wear resistance shows the very low improvement in corrosion resistance than the aluminum alloy. Okay, and parameters set like the 1500 rpm to 40 mm per meter minute, and second pass is selected for the further processing. Further processing means that suppose this technique is showing some results, so further processing means like you can follow some heat treatment process or addition of other reinforcement particle, because whatever you are not getting here, if you do some kind of other methods, you can add this some more extra properties in these composite materials. Okay, so that is the one case study I have highlighted here. So this is my talk only. Okay, so these are all references, and thank you.